So today I will be presenting a side channel attack. This allows you to count the number of packets sent between arbitrary hosts on the internet under some fairly common assumptions. Specifically, excuse me, for ICMP and UDP, we can count the exact number of packets that a Linux machine sends to some specific machine on the internet. For TCP, we can determine if some machine is connected or was connected to a Linux server. So considering the following scenario, you have some dissident from, say, Repressistan, who is living in the United States. They're accessing a VPN in the United States, but Repressistan has monitoring of all of the packets that go in and out of the country. Well, even though this dissident is posting to some blog even though the dissident is posting to some blog in Repressistan through a VPN server in the United States, through our side channel, Repressistan could still de-anonymize the user. Here's another one. You're a student, you suspect your advisor spends his nights looking at pictures of cats instead of reviewing your dissertation. You have a list of sites that you think he might be visiting, and chances are they're web servers, so they're probably running Linux. You can confirm your hypothesis using the side channel. So here's some background. There's a slight overlap with what I talked about earlier, if you saw that. But this technique also uses IP fragmentation. So packet spoofing, first of all, I think most people probably know what this is. This is just you send a packet with a return address other than yourself, some other machine on the internet. And again, IP fragmentation, this is if you have a datagram, you just split it up into chunks to send it over a thinner medium. IP reassembly, though, of course, fragments, they get lost, they get reordered on the internet. It's a tricky business. This is why end hosts, they keep fragments in a fragment cache in the hope that all of the fragments for the datagram that was originally split up will arrive and they can put it back together. Of course, these fragment caches only have a finite amount of space to store fragments, and this is the side channel that we'll be using here. The other side channel that we'll be using are IP-ID counters. So each IP packet that you send out over the internet, this has some number in it. This is so that if it gets split up into fragments, you can actually put it back together again, and you know which datagram the fragments originally belonged to. Now, there are different ways of assigning this IP ID. The good old-fashioned way was to use something called a global counter. This is just some global variable in the kernel. Every time it needs to send a packet, it just increments the global variable by 1 and sends that packet. So 10, 11, 12, and this is universally across all packets that it sends. But in the late 90s, though, we sort of discovered this is probably a bad idea. This leaks information. These things called idle scans were discovered. This allows you to do a port scan from the vantage point of some zombie without the guy that you're scanning even knowing that you're the one doing the scan. People thought, hey, this is a problem. So a lot of people tried to come up with different solutions to this. Linux took the following route. They use per flow counters for flow-based connections like TCP. So when you have a connection with someone, this connection has its own counter that's incremented, and these values are assigned to each packet. But it also has per destination counters. These are used for ICMP, UDP, and TCP packets that don't really belong to a flow. Well, our trick here is that we can actually measure these per destination counters values. And we'll see why that's a neat trick in just a little bit. So how do we measure these values? The first thing we do is we plant what's called canaries in our in basically our sort of target machine. We call this the other machine M, and we call the Linux machine L in this diagram. So we plant these canary fragments on M. These are spoofed from L, and these are just sitting in M's fragment cache. We choose the IDs of these canaries very carefully, though, as we'll see in a little bit. because the next step that we do is we then try to see how many of these canaries we can knock out. So we do this by sending large echo requests spoofed from M to L. Since these echo requests are so large, when L replies to M, we can be assured that they will be fragmented. Now, depending on the IP IDs in these echo replies that L sends to M, this may or may not knock out some of our canaries. So in this case, we have some staggered canaries in M's fragment cache. We've spoofed 100 echo replies, and we can see that 5 of our canaries have been knocked out because the actual value of the counter was somewhere within the range of the canaries that we tested. Now, how do we know how many canaries were knocked out? Well, to measure that, we have to perform this one other step. This time, this is actually the first time we're sending packets that actually are from us. So we send probes from us, a whole bunch of them. We plant them in M's fragment cache, as many of them as we can. These probes are typically, they can be echo requests, they could actually be oversized SYNs, basically any kind of thing that we can get to sort of solicit a response back to us so we can see if it's still in the fragment cache. Because the next thing that we do is we query these probes. Let's just walk through how this would work. If, say, all 3 canaries that we placed in the fragment cache are still in there, we would load in as many of our probes, in this case echo requests, the first halves of echo requests from us. Then, when we try to send the second halves of all of them, in this case, we get 7 of them completed, because 7 of them were able to fit in there, and so we get 7 responses. Now say, what if 2 canaries were missing, of course? Well, we do this again. Well, 9 fit in. So 9 of them are completed, and we get 9 responses. So this is how we can test ranges. This is how we can test ranges of values for the possible value of this per destination IP ID counter for M. Of course, once we can do this, we can do a binary search-like technique and search the relatively small 2 to the 16 value IPv4 ID space. So we do this. Now we know the exact value of this counter. Well, then how do we measure communication? Well, if you recall, ICMP packets and UDP packets, these are always draw from the per destination counter. So if we periodically check to see has this counter changed, we remeasure this counter, we can count exactly how many of these packets have been sent. TCP, though, if you recall, is a little bit trickier because it has these per flow counters. So the per destination counters aren't affected by the per flow counters, but we can still get some information to leak to the per destination counters by trying to get TCP packets to get sent outside of a flow. One naive way would be to try to send an ACK. In this case, if there is a connection, an ACK is sent from the per flow counter. If there's no connection, a reset is sent drawing from the per destination counter. Why is this naive? Well, typically if you're trying to measure if there's a connection, you know both addresses, you know one of the ports, but you probably don't know the other port. So you have to guess all 2 to the 16 ultimately. So the problem with this, though, is that if there is a connection, you will get it incremented by 2 to the 16 minus 1. If there's no connection, you'll get it incremented to 2 to the 16. Of course, if a packet is lost, you'll measure the exact same thing. So it's very hard to tell these 2 cases apart. So there's another way that you can use, and this takes advantage of the time-wait state. So TCP has this time-wait state. It's after the connection is closed. It's basically there to sort of suck up any stray packets that might be trailing in after the connection is closed so they're not mistaken for being related to a different connection. The way that this works is that we send SYNs, in this case, to the server. And if it's in a time wait state, it returns an ACK from the per destination counter because the flow is over. But if there's no connection, for whatever reason, Linux always returns synax with IP ID 0. So this actually isn't drawing from any counter at all. And in this scheme, the per destination counter only goes up if there is a connection, or in this case, if there was one. So we reported this issue to the Linux folks. Linus and friends got back to us pretty quickly, actually. They said that they had actually already done a change. But let me explain this to you. So they got rid of the per destination counters. Now they have 2,048 different counters. And depending on the address and a secret, you will get hashed to one of these 2,048. Well, like I said before, this was done even before we reported the issue. This was done for performance reasons, actually. It wasn't done with security reasons in mind. And we'll see it's actually both a good and a bad thing. So it's pro-anonymity insofar as it adds noise to these counters. This is good if, say, your server or what have you has a large pool of possible users that you're trying to distinguish, because now you have all of this extra noise. So if you see one counter going up, you don't necessarily know it was one specific address that was accessing that resource. It could have been one of a large number of people doing it. Of course, the con is that our side channel is no longer even necessary. If you're an attacker and you control thousands of addresses, they'll hash to most of these counters, and you can just read the counters directly by just sending the server pings and looking at the IDs that come back. So what did they do in response to our report? Well, they did two changes. The first is they changed the hash a bit. Instead of just the destination and some secret, it's now the destination, the source, and the protocol number. This might seem strange, but the protocol number was added in there to isolate the protocols in terms of which counter is being drawn from. So if you recall, we leak out the value of these IP ID counters through echo replies from the Linux server. So this is the ICMP protocol. If the UDP one hashes to a different counter, then you can't use our side channel to infer UDP packet send via our technique. But perhaps more importantly is they added some randomness. So now, before every access to a counter, they add randint of time since last access, where randint of n is some uniformly chosen random number between 0 and n. But this...
So what it is, or is it a linear congruential, nice, fast, easily breakable random number?
I hope it's not that. But that might be something to look into.
It's funny if they would spend a bunch of cycles per packet.
Yeah.
That's the fixer. Right, so it wouldn't surprise me if they did it on the sheet.
Right. Of course, even this is problematic because if there's a large number of packets being sent, this drowns out the randomness. If there's a small number of packets sent, this can actually still leave a signal, as we'll see here. So this would be, if there are no packets being sent, we were measuring every 100 time units, we would expect to see this randint of 100 distribution. But if there's even one packet being sent, and we're seeing randint 50 plus randint 50, we're already seeing a radically different distribution. 2 packets being sent, and as we increase the number of packets, this of course approaches a normal distribution. But the point is that a sophisticated attacker could probably tell whether he's drawing from this distribution or even from this one. So so these changes are actually already in kernels now. So by changes, I mean, the one I talked about before, where everyone's being hashed to 2,048 different counters, and the change to the hash and the addition of randomness. So this is in 3.16 and later. It's been backported to some older long-term releases. But of course, this is probably still vulnerable to people who have a lot of addresses. And as usual, if you're using a distro, your mileage will vary. So in conclusion, I don't know. So everyone says, like, SSL is broken. Well, I'd like to make the case that IP is broken. We can't even do layer 3 right, probably not layer 4 either. In IP's case, this really comes down to one thing, that all these IP stacks keep dancing around, and that's this RFC requirement that IP IDs must be unique for every in-flight packet. And when you have this kind of constraint that one packet can't have the same ID as one that was sent just a little while ago, well, now you have information flow, and that allows attackers to do these sorts of horrible things. So, thank you. How expensive? I don't have the exact numbers on hand, but like if you read the paper, it usually takes about 60 minutes to actually infer the initial value.
An hour?
Right. Now, that might sound like a long time, but this is a one-time thing that you do. This is like analogous to like setting up a wire trap. And then you use this to later determine, has anyone sent anything.
So it would be pretty noisy if someone's looking for it, but it's certainly feasible to do the pinpoint measurement. Putting aside it's noisy.
Right.
The other thing I was just wondering is your last comment about IPID. If everybody used MTU discovery, then there are no fragments.
Right. If you just get rid of fragmentation altogether, then you don't really need IDs anymore. Although there are some network appliances out there on the internet that have sort of overloaded the purpose of the ID, and they use it for things that they're not supposed to. But yes, in theory, in theory, if you're a service and you're never using fragmentation, you could just disable it altogether. Always send out ID 0 or something like that.
Thanks.
Mm-hmm. Thank you. Yes?
Can you use this trick for determining the sequence number between hosts? Because Linux also does this with sequence numbers as well as IP IDs, where it's per flow sequence numbers, or per destination sequence numbers, initial sequence numbers, and then increment with some timestamp after that. And if you learn that as a third party, you can do cross-site scripting injection.
Right. The answer is maybe. It's something we've actually put a lot of thought into. If it's possible, it's not something that's immediately obvious, though.